Hello everyone. The title of this video is Applying the Compound Interest Formula. So each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 6.1, called Exponential Functions, and I'm under the heading Applying the Compound Interest Formula. And each example I'm going to do is either taken directly from one of the examples in the reading, or one of the try it problems in the reading, or one of the exercises at the end of the section that's related to this particular objective. Alright, so I'm going to read, I'm not going to read this to you, but I will ask you to, if you're in this text on this website, read through this stuff. Talks about interest, right? Interest is, the growth of money. When you take out a loan and then you have to pay it back, with interest. It's like interest is almost like a fee for, borrowing money or keeping someone's money for certain periods of time. So I'm not going to get that in depth into what interest means, but this whole section here is about the growth of money, with compound interest. So here it is, the compound interest formula that I'm going to be using for every single example in this particular video. So compound interest, right? The amount of money that an account that grows with interest is worth, or the amount you owe on a loan with interest if you don't pay back anything at all after a certain period of time. So this is like, you put in put an initial amount into an account that pays interest. This initial amount is called P. It's called the principal, or the present value, or the starting amount. And then this formula tells you or shows you how much money would be in that account if that initial amount earned interest at a certain rate for a certain amount of time, compounding so many periods in a year. If you just left it alone, right? If you didn't throw any more money in, if you just threw the principal into the account and let it grow on its own without throwing any more in, what would the amount be after so many years? That's what this is telling us. So we have A of t equals this P times, and then an exponential expression, where the base here in parentheses is 1 plus r over n, r divided by n, and then the power is nt. See, the t is in the exponent, the input is in the exponent. That's why this is an exponential function. So A of t is the value of the account after t years, right? T is the time in years that you've had the account for. P, as I mentioned, this P out here is the initial amount of the account, the starting amount. It's often referred to as the principal or the present value. You'll hear those words, pretty much interchangeably. Or the initial investment. However, some initial amount in the account. R is the annual percentage rate, or APR. You may have heard APR talked about with credit cards before, or loans. This is also referred to as the nominal rate, as you'll read about in the text earlier. R is the annual percentage rate expressed as a decimal. Alright, so you got to pay attention to that. Don't write it as a percentage, which I'll get to with the examples coming up. And finally, N is the number of compounding periods in 1 year. Now that means how many times in a year is interest added to the account. Is it once a year, twice a year, 6 times a year, 12 times a year, 365 times a year, whatever. Right. So I'm going to be writing this out pretty much every single problem. We're going to fill in a bunch of the pieces, right? We're going to fill in values for maybe P or R or N or T and figure some things out. All right, so the first example I'm going to do is example 8. Now, I'm just going to read this out. What I've done on paper is I've written out what each number represents. Which variable in the formula does each number represent? So for example 8 here, it says, if we invest $3,000 in an investment account, so that $3,000 is P. It's the starting amount of the account, the initial amount, the principal, the present value. Paying 3% interest, that's the R, the APR. That's going to be this lowercase r. Now remember, I don't want to write 3 for R. I want to write 3% as a decimal. So 0.03, and I'll show you this in paper in a minute after I'm done reading. And this interest is compounded quarterly. Now compounded quarterly means every quarter, every 3 months. So how many times would that be in a year? That'd be 4 times in a year. That's what it means for compounded quarterly. So this gives me the value of N. N is the number of compounding periods in a year. If I'm compounding interest quarterly, that's 4 times a year. The value of N will be 4. How much money will the account be worth in 10 years? And 10 will be the value of T. T is 10, time in years. And we're asked basically what's A of 10, right? What's A of 10? What's the amount, the value of the account after 10 years? All right, so I have all that written out, as I said on paper here, right? The initial amount invested, the principal, the P, the present value, is $3,000 or just 3,000. The APR, the nominal rate, annual percentage rate, the interest rate for the year, R, is 3%. Now, like I said, you must write it as a decimal. So I'm not going to use the number 3. Remember what percent means. Percent means divided by 100. 3 divided by 100 is 0.03, right? Just take the number, move the decimal point, where it would be to the left 2 places. So this 0.03 is the value I'm going to replace R with. N, remember that was equal to 4, right? Because they said that interest was compounded quarterly, meaning that interest would be added 4 times in a year. All right. If it's compounded annually, that's once a year and would be 1. Compounded semi-annually would be twice a year and would be 2. Compounded quarterly is 4 times a year. You might see compounded monthly. That would be 12 times a year, n equals 12. Compounded weekly would be n equals 52. There are 52 weeks in a year. Compounded daily would be 365 in a normal year. We'll not use leap years. And yeah, so those are the ones you'll most likely see. And then we'll eventually get to a case in the next video, something called compounded continuously. What if n went to infinity? Now you can't plug in infinity, right? So that means we're going to need a different formula without n in it. But we'll see compounding continuously in a future video. And then time is in years. Time was 10 years. You had the account for 10 years. All right, so here was the formula again. I'll write it out here. All right, the amount, the value of the account after t years is the value of this exponential function. It's the principal. It's P times, then the quantity, here's your base, 1 plus R divided by N. Right, so the interest rate as a decimal, 0.03, divided by n, that number of times number of compound periods in a year, which is 4, compounded quarterly. And then the exponent is n times t. Right, n times t. So I'm just plugging the stuff in that I have, right? So the amount that the account is worth after 10 years is going to be 3,000, right? That was the principal, times, and then the base is 1 plus 0.03 for the interest rate, the annual rate, divided by 4, and then that's raised to the 4 times 10 power, or the 40th power, right? 4 times a year for 10 years. Basically, this power is just how many times interest got added in total. 4 times a year for 10 years. Right? And then we'll round this to the nearest cent, right? Dollars and cents. So basically to the nearest hundredth. And I'm going to go to a calculator for this. I'm just going to go to that Desmos site, desmos.com. Oh, this was from a previous video. I'm sorry. Go to desmos.com, and off to the side here, left side here, I'll just enter the calculation we're making. 3,000 quantity, and then 1 plus 0.03 divided by 4, close the parentheses, raised to the, I'll just put the 40th power, right? That was the 4 times 10, n times t. So if I put $3,000 into this investment account and left it alone for 10 years, it would be worth $4,045 and about 5 cents, right? If I round it up, because it's 0.045, I would round up to 0.05. And that's what I'll write here. Right? So after 10 years, this is in dollars, right? The account would be worth approximately $4,045 and 5 cents, and if I round to the nearest cent. And that's what they were asking in that example 8 in the text. Right, but it is, and I'll put this in a box, and I'll be writing this up every single problem. I would say get to memorizing this, just like the quadratic formula or something. This will be very important for all these problems. Now I'll make it a lot easier, of course, if you memorize it. All right. The next example. Now I have just some letters and numbers written out. This is actually coming from, it's coming from the text. Go back to the text here. This is coming from the very next problem, which is the try it, number 8. So an initial investment of $100,000, that's the principal, that's the P, the present value. At 12% interest, right, that's R, 12%. But I'm not going to write 12, right? 12% is 0.12, right, as a decimal. I'll write that. Is compounded weekly. So remember, there are 52 weeks in a year. So that's the value of that n, right? The number of times interest is added or compounded in a year. N equals 52. And what will the investment be worth in 30 years? So T is 30, right? And that's all I have written here, right? Principal, the present value, the initial amount, the initial investment was $100,000. The interest rate, the annual interest rate, the APR, the nominal rate, whatever you want to call it, is 12%. But as a decimal, what I'm going to be writing in the formula is 0.12. They said it was, compounded weekly. Right, so the value of n was 52, right? 52 times in a year, 52 weeks in a year. And the time is 30 years, right? What's the amount after 30 years? So what's A of 30, right? The amount, and again, here's the formula once more. I'll write it up for most of these problems. Principal times, and then the quantity, 1 plus interest rate divided by number of compound periods. That's the base, and then the exponent is the total number of compound periods, n times t, for the entire time. So the amount that this investment account will be worth after 30 years is going to be $100,000 times 1 plus, the interest rate is 0.12 divided by, 52, or compounding weekly. And then the power on this is 52 times 30. All right. Now that would be 1,600 times the interest was added, right? 52 times a year for 30 years. And we'll round this. I'll put this into the calculator. We'll round this to the nearest cent. So I'm really just changing some stuff up here. So I'll keep the same basically. So 100,000, the initial amount, that principal. 1 plus, not 0.03 for the interest rate, but 0.12. And we're not compounding 4 times a year. We're doing it 52 times a year. And it's 52 times a year for 30 years, right? Now I could just put up here 52 times 30. Maybe double parentheses, 52 times 30. And just make sure that's all in the exponent, right? Or you just put, the 1,600 power if you multiply them out. And yeah, and here we go. If I put this $100,000 into this account and left it alone for 30 years and it grew at the same nominal rate every year, we'd end up with, after 30 years, it'd be worth $3,644,675 and about 88 cents if I'm rounding to the nearest cent. And that's what I'll write. So again, this is in dollars, right? So $3,644,675 and about 88 cents. Right, and there we go. That is all we are asked for. Okay. Great. All right, so now I'm going to stop going to the text. I mean, I'm still pulling examples from the text, but I'm just going to go to my pieces of paper here, and we're just given certain information, asked to use the formula, and solve for certain values. Right, so in example 3, we're given this information. So let's just say these are investment accounts again, just to stick with the same kind of concept. So the amount that the account is worth after 18 years, right? This is the time here, right? T equals 18 years. So the amount the account is worth after 18 years is $40,000. The APR, the nominal interest rate, is 6%, which I'm going to write as 0.06, right? Don't write 6, but write it as a decimal, 6%, 6 divided by 100, 0.06. And then the n equals 2, that means that interest is compounded semi-annually, right? Semi-annually means every 6 months. So two times a year, interest is added. Now this is a little different from the previous two because we're given the final amount after 18 years. We're asked to figure out what would the present value or the initial amount or the principal, what would the value of P have to be? What would I have to invest in this account in order that 18 years later it'll be worth $40,000? So once again, the formula, the compound interest formula, A of t equals P times the quantity 1 plus R over N, that raised to the N times T power. Now I know, A of 18, so this is going to be 40,000 over here. All right, I know the final amount is 40,000 after 18 years. I don't know P, so I leave it as P. But I do know R, N, and T, right? I know everything else. So times the quantity 1 plus R is 0.06, divided by N is 2. And then the power is, 2 times 18, or 36. So if you want to simplify some things, you can. I mean, I'll use a calculator in a second. But we have P times, now half of 0.06, half of 600ths is 300. So this is 1 plus 0.03, really. This is 1.03 for the base. And then the power on this, 2 times 18 is 36. And then we solve for P. It's an equation that we can easily solve for P. Right. Over here on the right side, I have P times some number. So in order to get P alone, I simply have to divide both sides by that number, which is, whatever 1.03 to the 36 power is. And I do it to both sides. And there we go. I mean, there's our answer. I'll put it into a calculator, but we have P equals, whatever 40,000 divided by 1.03 to the 36 power is. And again, we'll round this to the nearest cent. So back to the calculator. Let's get rid of that. And we'll take 40,000 divided by 1.03 to the 36th power. So in order for this account to be worth $40,000 after 18 years, I would have to invest initially $13,801 and about 30 cents, if you round to the nearest cent. So this is what they're asking for here. So this is the amount you'd have to put into the account initially in order for it to be worth $40,000 18 years later, right? With this interest rate and interest being compounded semi-annually. All right. Great. So let's do another one like this. All right, so this time we're asked to find the final amount again. So this time we know the principal, the present value. We know the initial amount, the starting amount, $10,250. The APR, or the nominal interest rate, is 4%, which again I'm not going to write 4. I'm going to write 4 divided by 100, 0.04. Right. N is 12, right? Now when N is 12, that means, they told us that interest was being compounded monthly, right? Once a month. That's 12 times a year. And then the time that has passed is, 10 years. So if I invested, $10,250 into an investment account that paid this interest rate, compounded monthly, how much would the account be worth after 10 years? That's A of 10. All right, so this time I'm not gonna, I've written the formula 3 times now. You've seen it a bunch. So remember, this is the principal, 10,250, times, and then you have a base, which is 1 plus the interest rate, 0.04, divided by the number of times you're compounding in a year, which is 12. That's the base. And then the exponent is n times t, 12 times 10, which should be 120. And I can just punch this in, and we'll round to the nearest cent. So back to the calculator. So my initial amount, 10,250. Parentheses times 1 plus the interest rate, 0.04 divided by 12. And then all this raised to the 120th power, right? That's 12 times 10, n times t. So after 10 years, this account would be worth approximately $15,281.03. And that's what I've written out on paper here. Great. let's go again. Example 5, sorry. Alright, so this is similar to my example 3 from the video, where I know the final amount. I know the amount the account is worth after 5 years. So the amount after 5 years is worth $14,472.24. The annual interest rate, the APR, the nominal rate, again, whatever you want to call that, is 5.5%, which I'm writing as 0.055, right? That's 5.5 divided by 100. 0.055 is what I'm going to use. And then once again, n is 12, meaning that, interest was being compounded monthly. All right, 12 times a year. So I know everything but the original amount, the initial amount, the principal, or the present value. Right? All three of those mean the same thing: initial amount, principal, present value, P. And we're asked to round to the nearest dollar, right? Not the nearest cent this time. All right. So I know I didn't write the formula last time, but here it is again. Now you could also just take the formula the way it originally looked and solve for P right away. P, you just divide by this base in power. You divide by this exponential expression and get P alone. It would be the amount after t years divided by this 1 plus r over n to the nt power. And then I can just plug into this. All right, so the principal would be that amount after 5 years, right? $14,472.24 divided by, and then down in the denominator, I got the base 1 plus 0.055 divided by 12 raised to the 12 times 5, or the 60th power, right? T is 5, right? They said that this is the amount after 5 years, right? T is 5. And then I'm asked to round to the nearest dollar. So back in the calculator, again, that amount after 5 years is $14,472.24. Divide this by that base in power, 1 plus the interest rate, 0.055, divided by the number of compounds is 12 in a year, monthly, right? And then just the denominator raised to the 60th power, right? 12 times 5. And then rounding this to the nearest dollar would be $11,000, right? 10,999.6 would round up to 11,000. Right. And that's it. So I would have had to have invested $11,000 at this interest rate compounded monthly for 5 years in order for it to be worth $14,472.24. Okay. Again, I would highly recommend memorizing this formula for these problems. All right, so I got another one where we're just simply asked to solve the compound interest formula for the interest rate. Solve for R. We saw in the last example, the way it originally looks, you have A is solved for, the amount is solved for, the final amount. Here I solve for P. What I'm asked to do here is solve for R, get R alone. So once again, here's the compound interest formula. And I want to solve for R that's inside this base here, 1 plus r over n. That's the only place where r is. So first, if I were you, and I'd get this base in power alone, so divide by P. So we have A of t divided by P equals this base in power, 1 plus r over n to the nt. And remember, when the variable you're solving for is in the base, you can take roots. Remember solving like x squared equals 9 or something, you took a square root, right? I'm not doing that, but if the variable was in your base, you took roots. So I'm raising both sides to the 1 over nt power. So a of t divided by p to the 1 over nt power. Or you could call this the n times t, whatever that is, root of a divided by p. These mean the same thing. Equals, and then now that power's gone, you have 1 plus r over n. And then I would just subtract 1 and then multiply both sides by n. So we'd end up with this. R equals, the nth root, or the n times t root of a of t divided by p, and then we subtracted 1 from this and then multiplied all this by n to get r alone. So that's a fancy looking formula, but still it's the same formula as the beginning, but now solve for r. And that's it. That's all I was asked to do for that problem, but what I'm going to be using this for is in the final example I have. Okay, so in example 7, see, I'm asked to I'm given some information and I'm asked to find the interest rate, right? Find that nominal rate, that APR. So we're given the principal, right? So the initial amount, the principal, the present value is $5,500. Once again, the interest is compounded monthly, right? N equals 12 again. And the amount after 30 years, right? T is 30 here. The amount the account is worth after 30 years is $38,455. We're asked to now find the rate. And I can go and use my result from example 6 to do this. So I've got it written up here. So this will be, now n times t would be 360. All right, 12 times 30, that's 360. So the 360th root of a of t over p, the amount after 30 years over p, so $38,455 divided by $5,500. Then we subtract 1 from this, and then multiply it by 12. And this will give us our interest rate. All right, so I'm going to go to my calculator. All right, so in parentheses now, instead of writing the 360th root, I'm just going to do that to the 1 over 360 power. So I got 38,455 divided by 5,500, right, raised to the 1 over 360 power. All right, that's the 360th root of a over p. And then minus 1. Then I close the parentheses there, and then times 12. All right. So about 6.5%. Right, 0.065 is the value of r. And it's approximately 0.065, or 6.5% if I move the decimal place back to the right twice and write it as a percentage. There's your APR. Right? There's the nominal rate, the annual interest rate. If you start with this amount and end with this amount after 30 years and you're compounding interest monthly, the interest rate would have had to have been about 6.5%. Now again, you didn't have to use this formula here with the r equals. I mean, you could have started with this, plugged in a, plugged in p, plugged in n and t, and then solve for r. And you would have ended up with the same exact value though. Okay, great. Now you might be asking, well, what if they ask us to solve for t instead? We're not there yet. All right. Solving for a value in an exponent, that's going to take things called logarithms, which will be, we'll get to those later in chapter 6 of this text. But for right now, you should be able to find, a given all the other values. You should be able to find p given all the other values, and you should be able to find r given all the other values, using techniques and knowledge you have from previous sections of this book. All right, great. And I'm hoping that watching me go over these examples here help you out in some way when you're asked to apply the compound interest formula on your own. And thank you very much for watching.